on here. So hopefully everybody had a good break. Kind of just a little bit of a recap for you going where we're at. So we've got a Connect assignment that's due at the end of the week. We should have covered all that stuff before spring break. So hopefully you worked on it prior to spring break. Otherwise, we'll be kind of going back to some older material. The Excel was some old stuff, but it'll also be doing things from this week. We won't do Excel today, but Wednesday and Friday, both classes will do a considerable amount in Excel of how to do confidence intervals, which is what we're going to talk about today. And then we're supposed to have the kind of tentative exam date set at the beginning of the semester was next Friday. I'm going to push that to the following week on that Wednesday. So that gives us next week to go over hypothesis testing, do a review session that following Monday, and then kind of take that exam on that following Monday. So I'll get an announcement up on Canvas about that this afternoon. Other than that, any questions from me before we get started here? So that'll be like the 28th or around whatever that Wednesday date is. Let me see. I can look it up. What date is that? The 30th, that Wednesday. So got a couple weeks. We got some material to get through the next 2 weeks, and then we'll kind of be ready to take a break. We'll have some hypothesis testing on this exam, but also kind of pick back up after the exam, do some additional hypothesis testing. So what we're going to be setting up today, kind of we'll be using for really the rest of the course. Any questions before we jump into material here? Okay. So where we left off is we were taking samples, finding a sample mean or a sample portion. We then discussed what the distributions of those sample statistics would look like. All right. So we were going to use those sample statistics as the best guess of where the population parameters were. So sample mean was our best guess of where the population mean was. So what we want to do is we want to make sure there's no bias that exists in our sample. But we also want to reduce the variance on that distribution for our sample statistics. So why might we want to do that? So where we left off, we had the variance of our sample mean looks something like this. And then the variance of our sample proportion looked a little bit different because this numerator represented the variance of our population proportion. So we've got our variance and our sample proportions here. You can think about higher sample sizes would do what to the variance of our sample statistics? Yeah, decrease it. So why was that a good thing? Well, we said as long as we have a sample size over 30, we know our sample means will be normally distributed around whatever that population mean is. So if I can make sure that the variance is low, that gives me a much more peaked distribution or increases the probability of seeing values really close to that population mean. So that was kind of the thing we could control. Taking higher sample sizes, we could reduce the variance on that distribution of our sample statistic and make it more likely that we're going to see values from our sample that are really close to whatever the population parameter is. So that's kind of, I guess, a little bit of a summary or kind of some things that we had talked about and we'll kind of use as a jumping off point. So what we're going to try to do, or our goal with confidence intervals, is based off of our sample, we want to create a range of values that we can say, with 90% confidence, the true population mean is somewhere in this range. Right? So if we had something like this, maybe that true mean, and I think I used birth weight a couple times in the slides. So let's say the true population mean was 3,500. I take a sample, probably going to see something maybe over here. I then go a certain amount to the left and a certain amount to the right to create what we're going to call our upper and our lower bound. Well, I know that most of the sample means I see are going to be relatively close to that population mean. So when I'm creating these confidence intervals, there's a really good chance that if I go, pretty far to the left and the right of my sample mean, I'm going to have a range of values that includes the true population mean. Right? Excuse me. So maybe the sample mean I saw was like 3,600. Add and subtract 200 to that to get my upper and lower bound. And then that range of values, I'm saying, okay, with 90% confidence, the true population mean is somewhere in this range. Sure enough, it is. Okay, that's the idea behind what we're doing. But how do I choose that value? Like I just chose 200. It was kind of arbitrary just to give you an example or give you a number for the example. But we're going to eventually get to how do we choose that number. Right? So let me see. I think I skipped this in a second, but I want to give you an idea. So, oh, there we are. So, right, we're going to go a certain amount below and a certain amount above that sample mean to create this upper and lower bound for our confidence interval. Okay. So that's going to be kind of our best guess that the true population mean is somewhere in this range. Right? I think I skipped some of this. So yeah, here I kind of said, we could think about maybe I'm doing birth weights, right? So I take my sample mean birth weight, I build a confidence interval around that sample mean and say the true population means somewhere in this range of values. And I can do this with different levels of confidence. So I can build an interval of 90% confidence. I can build an interval for the 99% confidence. And those are our three kind of general benchmarks, 90, 95, and 99. It's just seldom that people want to say something with 82.3% confidence, right? We kind of have those three benchmarks. Now, if I want to say something with 90% confidence, so let's say I'm thinking about the average income in the US, right? If I tell you that with 90% confidence, it's somewhere in between $50,000 and $60,000. If I want to give you a range of values, and I want to say with 99% confidence, the true mean is within this range, well, it has to be true about my range. So if 90% confidence is between 50 and 60,000, the 99% confidence has to be a wider range of values, right? So when I want to say things with higher levels of confidence, that's going to change kind of the size of this confidence interval that I'm building. Okay? But how do I know how much to the left and how much to the right I need to go? Right? How do I choose that W? Now that's going to be our goal today. Okay. If I can get my slides to work here. There we go. So we can use what we know about the normal distribution in order to do this. Okay. So let's say I want to build a 95% confidence interval. Right? I've got some things in the slides, but I'll probably be doing a lot of this on the doc cam here today because I think it's better to see me build a lot of this stuff. So I don't use this blue marker. Let's say I want to build a 95% confidence interval. So we're going to kind of diverge a bit, and then we'll eventually get back to building that confidence interval. So if I think about my standard normal distribution, right, or those are my Z values, right? We know that Z values are standard normally distributed. We can convert different normal distributions into a standard normal distribution by turning them into Z scores. And I know that a standard normal distribution is centered around 0. Right? I actually probably should say that this is the Z score mean. There is going to be some Z score that I could choose. So go a certain number of standard deviations above and below, such that the probability, I guess I'll do it here, the probability I see something within that many standard deviations above and below is 0.95, or 95% chance I see a sample mean that's somewhere in between a certain number of standard deviations above and below the true population mean, which means what percent chance is there I see something that's further from the true mean than that number, or sorry, what's the probability that I see something a further number of standard deviations away from that population mean? Well, 95% chance that I'm in between this range, the total area kind of outside that would be 0.05. But that's the total area outside of that range. And we're going to end up calling this alpha. And I'll go into that a little bit more in a second. So if alpha is the total area outside that range, half of alpha would be in each of these tails or on each side of my range. So we can use the inverse process, right? We know we want a 95% confidence interval. So we want to find the Z value, or the number of standard deviations above and below the population mean we need to go to get the probability that I'm somewhere in between this number of standard deviations above and below to be 0.95, matching up with that 95% confidence interval. Well, because the area under the curve is 1, we know the total area outside that range would be 0.05, and there would be half of that on each side, right? So 0.05, if we're referencing that as alpha, there would be half of alpha on each side. Well, I can do this, and we've already done this. This is the inverse process, right? We've already learned this, where I know the area in the tail I want is 0.025. I can find that corresponding z-value by using my standard normal or my z-tables. So the area I want in the tail is 0.025. So I'm going to scroll down here. I'm going to try to find that value. Looks like it's exactly right here. So the z-value that would give me 0.025 in the tail is negative 1.96. So I just looked that value up, negative 1.96, which if negative 1.96 gives me 0.025 in the lower left tail, that same z-value, but positive, would give me 0.025 in that upper right tail. So I can find this z-value, this number of standard deviations where I need to go to get that targeted confidence level I wanted, that 95% confidence, which corresponds to a probability of 0.95. So that's kind of what we've already done. This is just using the inverse process. I can find that number of standard deviations. Okay. So with that in mind, if I'm thinking about the distribution of my sample means, I know that they're going to be, distributed around whatever that true population mean is, even if I can't see it. As long as I have a sample size over 30, my sample mean should be normally distributed around whatever that true population mean is. Okay? And then I also know from up here that if I go 1.96 standard deviations below, and what standard deviation, well, I'm looking at the distribution of my sample means, so it needs to be the standard deviation of my sample means. If I go 1.96 standard deviations above and below that true population mean, the probability I see something or see a sample mean somewhere in that range, well, if I'm 1.96 standard deviations above and below, those would correspond to those z-values of negative and positive 1.96. So what ends up being true is if I start to take samples, so let's say I take a sample mean, all right, sorry, I take a sample, I guess, and this is the first sample mean that I see. I then go a certain amount to the left and to the right, and that amount that I'm going to go is I'm going to go 1.96 standard deviations above and below that sample mean that I found. Well, notice this sample mean value is less than 1.96 standard deviations below the true population mean. So if I then go 1.96 standard deviations above that sample mean value, my upper bound will be past that population mean, right? So if I go back 1, but forward almost 2, I'm going to be at a value that's further or past that point. If I then were to take maybe another sample over here, and I do the same thing, right? And I add and subtract 1.96 standard deviations from that sample mean. Well, once again, I'm less than 1.96 standard deviations above. So maybe I'm 1.8 standard deviations above. But then if I go back 1.96, well, now I've had an upper bound that's going to be past that population mean. So notice for any sample mean in this range, everything here is less than 1.96 standard deviations away from the population mean. So when I build my confidence interval around any sample mean value in this range, all my confidence intervals will include that true population mean. So 95% of the time, like I know that there's a 95% chance I see a sample mean somewhere within 1.96 standard deviations above and below. So 95% of the time when I'm building confidence intervals around my sample mean, it'll include that true population mean. Now the problem is, if I see a sample mean way out here, well, this is like 2.5 standard deviations above. So when I build my upper and lower bound, kind of ran out of room here, but I'm only going 1.96 standard deviations below this point, but it was like 2.5 standard deviations above my population mean. So I'm going to get a lower bound that doesn't quite capture that population mean. So for every sample mean value in my tails, when I build confidence intervals around those sample mean values, it wouldn't include the population mean. But I know that the likelihood I see something way out here, well, that probability was only 0.05. So I'll be right with 95% of my confidence intervals. I'd be wrong with 5% of them. if I just kind of kept taking sample means or samples over and over and over again. So that's why we call it, like, when I build my confidence interval around my sample mean, that's why I'm saying I can only say this with 95% confidence. I'm going to be wrong 5% of the time, but for 95% of the sample means I could see, my confidence interval will include, the true population mean. So that's the idea behind what we're going to be doing, is we're just going to create these confidence intervals, even though we know they will be wrong sometimes, right? But we're letting people know that, right? We're telling them, like, with 90% confidence, with 95, with 99%. Right? So that should line up with, let me see there, what I have on this slide. All right, and that 95% of the time, our confidence interval would include that true population mean. Okay. Any questions up to this point? So we're kind of going through the conceptual part. We'll kind of get to the computation, some actual problems here in just a second. Okay with this for now? Okay. So I kind of already referenced this, but right, this idea of alpha, and there's, you kind of think about alpha is really the probability that we make an error with our confidence interval, that it actually doesn't include the population mean. A less technical way to remember what alpha is it's the percent outside your interval in decimal form. So if I've got the 95% confidence interval, the area outside my interval was 5%, in decimal form, 0.05. 90% confidence interval, area outside my interval would be 10%, in decimal form, 0.1. So what would my 99% confidence interval alpha value be? 0.01, 1% outside the interval, decimal form, 0.01. What about the 83% confidence interval? Yeah, 0.17, right? 17% outside and decimal form 0.17. So this is how we do that. Now we can work in either direction. So you could use this equation to work in the opposite direction. But I think it's just intuitive. Like if we think about it, it's a decimal form of the percent outside interval. So let's say, you have the an alpha value of 0.07. What would your confidence level be? So there'd be 0.93 in the interval, and a percentage would be 93%. Right, so that's all this equation is doing. It's just working in the opposite direction, right? So we'll typically use these three benchmark values. So we'll kind of have the same pairs of, like, you won't really have to mentally probably go through this every time, because you're going to start getting used to, like, oh yeah, 95% alpha is 0.05, 90% 0.1, 99% 0.01. Okay. So we'll be using these benchmark values a lot. And what I kind of already alluded to this, but our confidence interval equation is going to be, we're going to take our sample mean, and then we're going to add and subtract a certain number of standard deviations with this z value. Well, if I want to go 2 standard deviations away, I then need to multiply that value of 2 by whatever the actual standard deviation is, right? If the standard deviation is 100, that means go 200 to the left and the right. If the standard deviation is only 20, or sorry, if the standard deviation is only 10, that means go 20 to the left and the right, right? So I'm going to go a certain number of standard deviations to the left and the right of my sample mean to build my upper and lower bound. Now, why does this say the z-score for alpha over 2? Well, remember, what we were doing was, once we knew the confidence level that we wanted, we figured out what alpha was from that, right? 95% confidence would be an alpha of 0.05. That means I would have half of alpha, 0.025 in each tail, which is why we start writing, like, I want the z-score for alpha over 2, or the z-score for 0.025. So sometimes the way I'll start writing this, if we know the area we want in the tail and we want to find the corresponding z-score, I'll write like the z-score for whatever that corresponding area in the tail is. So we're always going to be using kind of that z-score for having half of alpha on either side of our confidence interval. But once we look up that z-score, it's really just a matter of plugging values in. So we'll put some actual values to it here. We'll skip this for now. So I'll come back to this later. So let's work through an example. I've got a couple things that I'll mention along the way. So if you've got some questions, maybe hold off for just a little bit, because we're going to be doing some things that might seem a little hokey at first, but I'll explain them away, I think. So let's say we've got hockey puck production, right? And it's producing all these, one after the other, and they pull 49 of them off the assembly line and they weigh them, right? So they sample 49 of them, and they find a sample mean weight of 7.5 grams, right? somehow someone tells us that the production process itself has a variance of 49. So this process that we're sampling from, the original variable, has a variance of 49. Right? And I want to build a 99% confidence interval for what the true population mean weight of these hockey pucks is. So let's go write down everything we know. So sample mean 7.5, sample size 49, sample variance is 49. And if I want the 99% confidence interval, what should my alpha value be? 1% outside in decimal form, 0.01. So we just identify everything that we need. The next thing, if we looked at this confidence interval equation, walk through a couple things here. Well, first of all, when I'm writing this plus minus, I really every single time could write out the equation for my lower bound, which is to subtract what's on the right here. And my upper bound would be when I add what's on the right there. But just to kind of shorthand it, since it's the exact same thing, just add to get your upper bound, subtract to get the lower bound. It's really representing two equations. Now, one thing that I'll start using is some terminology, and it's not technically correct since we're not dealing with proportions yet, but it makes life a lot easier to reference this thing instead of just saying this thing on the right. I'll start referencing this as our margin of error. Okay. Just makes it a little bit easier. Like I said, it doesn't really have necessarily a margin of error interpretation unless we're dealing with proportions, but makes it easier to kind of keep that terminology consistent. So another way of writing out this equation is the standard deviation of our sample means. Well, we know that that's the square root of the original variance over our sample size. So we could just substitute that formula in and do all the work at once when calculating our upper and lower bound, or we can find the intermediate value and then plug that in. Either way is okay. Right? Both ways will give us the right answer. I usually walk through calculating this intermediate step just because it gives us an idea about what the standard deviation on that sample mean was, and that becomes helpful as we kind of work towards like hypothesis testing. So really at this point, to calculate our confidence intervals, I can plug in my sample mean value. Even if I do the intermediate calculation here, so this is what the square root of 49 over 49. So I get this value of 1, right? Which I could do this all at one time, or I could, plug it in. The only thing left I need to find is that z value, the number of standard deviations away I need to go to get my upper and lower bound. So if I wanted the 99% confidence interval, that was an alpha of 0.01. So when I'm thinking about the number of standard deviations away I need to go, or my z value, I'm trying to find the z value that gives me an area of alpha total in each of these tails. So my alpha is 0.01. I'm going to have half of alpha in each tail, or 0.005, right, on each side of my confidence interval. So the area I want in the tail, 0.005, I can use my standard normal table to look up and see what that z value is. Okay. So I go to that z table, and I try to find 0.005. These are the two closest values. Right? So negative 2.57, negative 2.58. I'm in between those two. I kind of said prior to spring break, that if we're in between, we'll just use the higher of the two in absolute value. So negative 2.57, negative 2.58, we would use negative 2.58. Or if I want to go out to the third decimal, I could do negative 2.575 if I wanted to. But if we're restricting it to two decimals here, we just found this was negative 2.58. Now, if negative 2.58 gives me 0.005 in that lower left tail, positive 2.58 would give me that same area of 0.005 in that upper right tail, right? Since this is a symmetric distribution. Now, another way I could, so first of all, are there any questions on anything up to this point? Going back a ways or rephrase something. Okay with this so far? So another way I could do this, if instead of looking up alpha over 2 and getting the negative value, if I just wanted the because you'll notice like the positive and negative, are already built into our confidence interval equation, right? We're going to go 2.5 standard deviations above to get our upper bound and 2.58 standard deviations below to get our lower bound, right? So I can look up alpha over 2 and find the negative value, or if I want to find this positive 2.58, if I know there's 0.005 in the upper right tail, what would the area to the left of this value be? 1 minus that. So I could look up 0.995 and hopefully I find positive 2.58. So if I look up 0.995, somewhere down here. Oh, I need to 0.995. Hold on. 0.99. Looks like I'm in between these two values, 2.57 and 2.58. Yep. So I would find 2.58 if I did it that way as well. So there's really two ways of doing that. I personally think it's just easier to look up that alpha over 2 value and then just remember, oh yeah, I found the negative value. I found what I needed to, need for the lower bound. The upper bound's the same thing. I just add. But once I have this 2.58, that was the last thing I needed. Now it's just a matter of getting everything plugged in. Okay. So got a lot of arrows going on. So let's look here. I've got kind of a summary here. Here's like our summary steps. Identify the piece of information you were given. Look up that Z value that gives you your alpha over 2 on each side of your interval. You can calculate the intermediate, like the standard deviation of your sample means, kind of do that intermediate step if you want, or you can do it, like I kind of show you can substitute that formula in and do it all at one time. And then it's just a matter of plugging your values in and then kind of getting it, doing the computation. So we identified all the information we were given. We looked at that Z value. Excuse me, I think I even showed you if you wanted to do the intermediate calculation here, the standard deviation of our sample means was 1. Plug everything in and subtract to get our lower bound and add to get our upper bound. So what we have, so that's kind of the computation side of things. Right? So are there any questions on that before we keep moving? Okay. So I have an upper and a lower bound of what? 4.92 and 10.08. So with 90% confidence, I can say the true weight, average weight of these hockey pucks is somewhere between about 5 and 10 grams. Right? So how do I use my confidence intervals? Like, sweet, I can find the upper and lower bound of his confidence interval, but like, what does it tell me? Right? Well, really what my confidence interval is saying is that with 90% confidence, the true population mean could be any one of these values. It's somewhere in this range between about 5 to 10. Okay? So if a company comes to me or they're putting out there that their hockey puck weighs 12 grams, based off my sample, I could go to them and say, well, with 90% confidence, no, it doesn't. With 95% confidence, the true average weight of your product is somewhere in this range of 5 to 10. Now, if they said, it's 8 grams. Well, remember, I think the sample mean we were looking at was 7.5, which is different than 8, but based on my confidence, not different enough to say that the true mean couldn't be 8, right? But based off the sample I saw, when I built that confidence interval, it was different enough from the value of 12 to be able to say, yeah, 12 is not one of the possible values for that true population mean. I can't see the population data, but based off the sample I found, with 90% confidence, I can tell you it's somewhere in between 5 and 10. Okay. Any questions on that? I'll probably go into a lengthier discussion here in a second about how we interpret the confidence interval after this next example. So go skip this example because I don't think we'll have time to do both. I don't like this one as much. So let's skip forward. I'll do this one, right? So let's say we went over to the rec center and we grabbed 35 of their 45-pound weight plates. Right? So we start weighing them, the production process, they're using several types of metals. They don't get the same consistent pour in every mold. So you weigh one, it might be 47 pounds. You weigh another, it might be 44. You weigh another, it might be 45 and a half. So we start weighing them all and we find an average of 46.5. Well, even if the true population mean was 45 pounds, it is possible we see a sample mean that's a little bit off of that. And we're not that far away, right? Just 1.5 pounds here. So based off the sample though, can we say that the true population mean isn't 45? Right? Because even though it's not very far away, maybe the standard deviation is really small. And so maybe, if we take a large enough sample size, like maybe we can actually get a really narrow range of values that doesn't include 45. I don't know. But that's what we're going to see. That's what we're going to try to do. Okay. So someone tells us that the population variance on this production process is 25 pounds. Now, this is where it gets a little hokey. So we've got a similar steps to the last problem. But remember, what are we doing with confidence intervals? We're using our sample mean to get a range of values for our best guess, or our best estimate, shouldn't say guess, best estimate of where the true population mean is. Well, if I don't know what the population mean is, how the hell do I know what the population variance is, right? If I had the population data to calculate the variance, why didn't I just calculate the mean? So the answer for now is we have to walk before we can run, right? So we're going to start with these examples. They're not the most practical, but it uses things we've already talked about and is a good starting point to then introduce something that makes it a little bit more complicated. So we're starting out assuming we know the population variance. In practice, we probably don't. Like if I don't know the population mean, I probably don't know the population variance. The examples where it's practical are the ones like I'm trying to use today, even though, hockey puck and weight plates seem pretty stupid, right? It's something where I can't pull every product off my assembly line, but I can sample some of them. And then, so I'll have a sample mean. I won't know the population mean, but based off of the machinery I have, so the engineers and, based off of physics and whatnot, they come up and they tell me, look, this machinery will have a variance on this production process of 25. Like based on what we know about the weight of the metals that you're using to, mixing together, pouring into these molds, we know the variance will be 25 pounds. So that would be a situation where it's, we would actually see something like this pop up, where my production process, my machinery, I know the variance on the machinery, but I'm trying to make sure that my product is hitting that targeted average. And I can't sample every single product I'm producing, maybe only like 35 of them. So we've got to walk before we can run. We got to understand how to do these examples before we move on to the next thing, which is a little harder, which is we don't know what the population variance is. Okay. So that's the setup. And, these examples seem trivial, but if we're trying to think about any product where we're targeting weights or we're targeting an average number of particles or something, it doesn't really matter that much to our lives if it's 45-pound weight plates, but if it's like some type of medicine, right? And you're trying to hit a targeted weight on whatever, the substance is, or some steel beam that's supposed to support like a huge building, we want to make sure we're hitting the targeted, population mean there for those products. So I think, pretty relevant, but let's actually work through and actually do the computation. So we've got what? Sample size, 35. Sample mean was 46.5. We're told the variance on the original data or the production process was 25. And we want to build a confidence interval that corresponds to an alpha of 0.1. So what would this confidence level be? Alpha is 0.1. Yeah, there'd be 0.9 in my interval as a percentage, 90%. Okay. So we can work in either direction there. Now, if I think about what I'm doing with my confidence interval equation, I'm adding and subtracting the same value to get my upper and lower bound to that sample mean. So my sample mean should always be smack dab in the middle of my confidence interval. So if I'm looking at these potential answers, which one can I rule out right away? The sample mean I found was 46.5. It's not even in this interval, right? So I did something wrong with my calculator if I get a confidence interval where my sample mean isn't even in it. I mean, it should be smack dab in the middle, let alone, it should not be, shouldn't be outside of that. So we can rule D out right away. The other ones all look reasonable, so we actually have to do the computation. So, oops. Go back to this in a second. So we've got all the information we were given. We could do the intermediate step here, which is calculate the standard deviation of our sample means. So this is what? Square root of 25 over 35. I can cheat. I know this is about 0.84. I can't remember exactly. There's more decimals, and we'll see in a second on the slides, but it's about 0.84. So I could then plug that in. I can plug in my sample mean, The only thing left I need to find is that z-score, right? So if I want the 90% confidence interval, that corresponds to, I want a z-score that gives me a total area to the left and the right of what, 0.1. So how much is going to be in each? Well, half of that. So 0.1 over 2 is 0.05. So I'm going to look up 0.05 in my table, and that should give me the last thing I need, which is that z-score. And that gives me half of alpha on each side of my confidence interval. So do that. So we'll look up 0.05. So looks like it's in between these two values here. So negative 1.64, negative 1.65. We use the higher and absolute value of the two. So negative 1.65. That was the last thing I needed. And remember that positive and negative are kind of already built into that confidence interval equation, right? I want to go 1.65 standard deviations below to get my lower bound, 1.65 standard deviations above to get my upper bound. Okay. And from there, it's just a matter of computation. We've got everything we need to plug in. So 46.5 plus 1.65 times 0.84. That's my upper bound. 46.5 minus 1.65 times 0.84 to get my lower bound. Any questions on anything there? So I think I have, oops. Yeah, so we can kind of walk through all the similar steps, plug everything in. We get about 45.11 for my lower bound and 47.89 as my upper bound. Okay. So it's going to look something like that. So with 90% confidence, I can say the true population mean is somewhere in that range of values. I don't know which one it is, but it's one of those values. Right? With 90% confidence, I can say that. Which, if this is the confidence interval for 45-pound weight plates, why is this a problem? 45 isn't one of the possible numbers in there, right? So I could go to that company and be like, yeah, based off of my sample, I mean, unless it's really biased, which, you know, I just randomly selected the plates, like your product isn't hitting its targeted goal, right? You know, it's close, like it could be close. The true population mean could be, oops, 45.11, but with 90% confidence, I can tell you it's not 45, right? And so, you know, this would be an example of where, like, you know, we got to change something, right? We found that our confidence interval does not include the value that we want. Okay. Questions? You know, and I'm using like these weight examples. You can imagine, like, maybe I'm just interested in the someone, I don't know. Sometimes people say things to me, and I just like that is completely false. Like, you're so far off. Like, I don't know. Like, oh, the average income in the U.S. is 60-something thousand. It's like, there's no way. So, like, you could always just go out and take a sample, build a confidence interval, and then tell the person, like, yeah, based off my sample, you're definitely not right. 95% confidence, right? You're not right. So we can do this really for anything where we're interested in what that true mean is. So that's how we interpret or we use these confidence intervals. But there's something I think maybe to sell, oops, exactly what we're doing a little bit better. So we have this equation for our confidence interval. And this is the slide that I skipped earlier. So I'll kind of show you where it's at after I'm done with this discussion. But so here was our confidence interval equation. And then we said we could just substitute in that equation we had for that standard deviation of our sample means, so that it looks something like this. Okay. Remember, I'm going to refer to this as the margin of error. So what are some things that will change the size of our confidence interval? Right? So remember, the reason why we care about the size is because I'm trying to give you a range of values for what the true population mean is. Hopefully that's a small range. Telling you that the average income in the US is somewhere between $10,000 and $110,000 is not helpful, right? Telling you it's between 53 and 55,000, it's a little bit more helpful, right? So I want to try to get a narrow range of values. Okay? So what happens if the original data just has a higher variance? Well, if the original data has a higher variance, that's going to increase my standard deviation from my sample means, right? So this goes up. Standard deviation of my sample means will also go up. My margin of error is larger. What happens to my confidence interval? It's wider. Okay? And that kind of makes sense. Like if I have a wider or a higher variance on the original data, well, my sample means are going to be all over the place. So I'm going to have to give you a much wider range of values to kind of capture what that true population mean is. Now, we can't do anything to control that. It just is what it is. The thing that we can control is what if I have a higher sample size? So if I have a higher sample size, and actually I'll start to do this in color so we can kind of keep track of my arrows here. If I have a higher sample size, what happens to that standard deviation of my sample means? It's going to go down. We said high sample sizes gives me this like really peaked distribution. So if my standard deviation of my sample means goes down, what happens to my margin of error? It's getting smaller. If I add and subtract a smaller amount to my sample mean, and I did write narrower on the other sections, but I feel like that can't be grammatically correct. So a more narrow confidence interval, right? If we take a higher sample size. So once again, I said this will start popping up a lot every topic we go over. Higher sample size is a good thing, right? Because it's allowing me with the same level of confidence, right? The Z value didn't change at all. The alpha didn't change. Just taking that higher sample size, I can say this with the same level of confidence that the true population mean is within a much narrower range of values, much more narrow range of values, okay? What if, and like the opposites of these are true as well, right? If I take smaller sample sizes, it becomes wider. What if I want to say something with more confidence, right? So you can think about this, I'm moving from 90 to 99% confidence. How is that going to change my confidence interval? Well, I can give you the intuitive result first. If I want to say something with a higher level of confidence, what has to be true about the range of values I'm giving you? With 90% confidence, I tell you the average income is between 50 and 60,000. If I want to tell you a range, I can say with 99% confidence, it's in between these two values. I have to give you more values, right? So I have to give you a wider confidence interval. Now, the math and what we know about the normal distribution, that plays out as well, because more confidence, what's going to happen to alpha? If I go from 90 to 99%, alpha actually goes from 0.1 to 0.01. So alpha is going to go down. Right? If I think about when I'm looking up my Z value, right, that Z value corresponds to alpha over 2. Well, let's say before, here was my Z value that gave me, I don't know, half of alpha, so 0.05. Well, at my new level of confidence with the lower alpha, maybe alpha now is only 0.005, I would have to use a Z value that's larger, right? When I say larger here, since it's negative, larger in absolute value, like a greater magnitude Z value. So when alpha goes down, I want a smaller area in that tail. That would correspond to a larger Z value. I'm using a larger Z value. My margin of error is getting bigger. So here, my confidence interval would be getting wider, right? I'm larger margin of error. I'm adding and subtracting a larger value. I get a wide, and that makes sense intuitively too. If I want to say something with a higher level of confidence, I have to give you more values, a wider range of possible values. So the goal behind confidence intervals, what we're doing, the things we can control. We can't control this, so that's out the window. If we want to be able to say things with high levels of confidence, like I said earlier, I want a narrow range of values. Well, if I told you the average income in the US is between 53 and 54,000, but I'm only telling you that with 1% confidence, right? Making a really low level of confidence, so I get a really narrow. Well, that doesn't do anyone any good. So what we want to do, say things with a high level of confidence, which we know is going to make our confidence intervals wider. So how do we combat that? How can I still say things with a high level of confidence? Make it a narrower range of values by increasing my sample size. So to be able to say things with a high level of confidence, but keep that range of values, that confidence interval pretty narrow, I need to start taking higher sample sizes. So in practice, like that's the goal behind what we're doing. Okay. Any questions over anything here? So next class, we're going to be doing all of this, but in Excel. So I've already got the Excel file up there. And then we're also going to I'll introduce the idea of building confidence intervals for proportions. The other thing that I wanted to mention, that if you want to do this, this is an optional thing, but I will be putting an announcement and putting this up on Canvas with a link. So I have a sports econ course, and typically what I do with them is have them all fill out a tournament bracket for the NCAA basketball. And then if anybody can beat my bracket, I then give everybody like a handful of extra credit points that go towards your online quizzes. So I decided I had one created on ESPN. So I'll use the ESPN kind of, I guess, it's not an app, you can go online as well. You can register through that. And then if anybody can beat me, which chances are very high, that someone, if you all do one, probability that somebody gets better than mine is like almost 100%. So I'll put that link up there if you want to do that before the kind of main games start Thursday. I'll have that opportunity up there, kind of a fun thing. I figured since I'm doing it for my other class, I might as well just do one for you guys. Pretty easy, pretty low cost. But other than that, I will see you guys on Wednesday. Enjoy the weather. Office hours are as normal this week. If you have any other questions, feel free to shoot me an email.